Hello everyone, I am Sanjeev from Structural Mechanics and Dynamics Laboratory. I am a third year doctoral student under the supervision of Professor Jidan. So today I am going to introduce my research, which is basically the post-earthquake damage classification of regional buildings using machine learning. So in this class, I am trying to cover these four main contents, starting from backgrounds and motivations of this study with some literature review, and then in order to utilize the machine learning techniques for damage classification, the most important thing is the data. So here I'm trying to generate data in order to train the models utilizing the ETAPS finite element modeling software, and then at the end, utilizing those generated data, I'm trying to use artificial neural network for the demonstration for this study in order to classify the buildings damage into different categories. So as you have noticed that from 2015 Nepal earthquake, 2023 Morocco and Turkey Syria earthquakes, it is reported that millions of people they have become homeless after the earthquake, and it is mainly because of two reasons. One is, of course, their buildings are heavily damaged or collapsed, so they cannot utilize further. The next case is they have their building standing, but they don't know the damaged condition of the building structures. So people they are forced to live outside the buildings in a temporary shelter for some days or even a month. Generally, the visual inspection method is carried out in order to assess the damage to the building structures after the earthquake. However, this method is a time consuming method, as we can evidence from the past earthquake, which is 2015 Nepal earthquake, 2017 Mexico earthquake. It took large amount of time in order to collect the damage condition of the building structures, and that will eventually delay in the decision making. Next is we need to mobilize large amount of the experts to the sites immediately after the earthquake for damage assessment. However, we may lack the experts to be mobilized to the sites after the earthquake. The next one is these methods sometimes contain uncertainties or missing details. For example, if we see the CTP buildings in New Zealand, it was inspected several times after 2011 earthquakes and declared safe. However, soon it was collapsed and 115 people died. If we see the write down figure here, then after the main shock of 2015 Nepal earthquake, hundreds of aftershocks were reported, including 6 to 7 magnitudes aftershocks. So in that case, it's very difficult to go inside the buildings and carry out the inspection work. Recently, significant progress has been made utilizing AI and machine learning for damage detections, which can be evidenced with the development of these research papers in different publications. In my research area, I'm also trying to utilize the same techniques, machine learning techniques, in order to classify the building damage after the earthquake. So basically here I'm using different types of data sets. One is the damage data and another is the image based data sets. So utilizing the damage data sets, I'm trying to use different widely used machine learning algorithms, and utilizing the image data sets, I'm trying to utilize different deep learning architectures, including the pre-train, the deep learning architectures. And at the end, I'm also trying to check the feasibility of using quantum enhanced machine learning or the deep learning techniques, utilizing both the damage data and the image data sets. So for this study, I'm only considering the damage data that we are trying to generate by using the ETAP software. So for that, when we try to revise the literature, then I realized that some of the researchers they only consider the ground motion features, or some of the researchers they only consider the structure or features in order to train the models and have the damage predictions. However, considering only one of those have uncertainty in the seismic damage predictions, and the applicability of the machine learning models will be limited. So in my study, I'm trying to utilize both the structural features and the ground motion characteristics, and using the same machine learning based techniques in order to predict the damage condition of the building structures after the earthquake. So for the so in order to train the models, the first and most important thing is the data. So there are different ways to collect the damage data. For example, the most important is like it's better to use the real world damage data sets, which is more realistic and gives the more realistic damage predictions after the earthquake. However, the collection of the real world damage data sets is tedious and difficult, and sometimes they have very limited access to the public in order to carry out the research, or let's say the train the models and have damage predictions. And the real world damage dataset also contains sometimes the imbalanced datasets for different classes. For example, like they have higher damage data for the no or very slight damage case, and for the very heavy damage, the collapse case may have very less datasets. So having the imbalanced dataset in the training, like the prediction results with bias towards the higher damage datasets. And so in that case, we can use the simulation datasets. For example, we can build the balanced datasets for each damage categories. And for example, like you can use the finite element modeling techniques in order to have the simulation datasets, or maybe I think you have already learned in the structural dynamics class, we can use the multiple degree of freedom models and the nonlinear time history analysis in Python as well. So for this class, I'm trying to use the finite element software, that is ETABS, which is famous for building analysis and design. And so in the ETABS software, I will try to show you a demo, like considering the time history analysis and how to get the data from there. Okay, so let's do a demo. So for that, I have developed the very simple architectures of the building structures. So where we can see that it is a now a 5-story building structures, and I have given the height for each story as the 3 meters. So the total the building height is around 15 meters. Then after that, I have also defined the material properties as Fe 500 for the steel and M30 for the concrete. Then I've also defined the section properties. For example, the frame sections. For the beam, I'm trying to use 350 by 350 mm, the cross sections, and for the column, I'm trying to use 450 by 450 the cross sections. Okay. So cross sections. Similarly, I have also tried to define the slab sections as 150 mm, right? Okay. So after that, we can I think maybe some of you are already familiar with the ETABS software. We can define many load cases and load combinations, for example, like wind load, earthquake load, dead load, slide load, and so on. So here what I'm trying to do is I'm trying to use the time history analysis functions in the ETABS, and then extract the results after the time history analysis, and then we use those data in order to train our machine learning models. So for that, for what we do is first we go to define, then function, then we go to the response spectrum. So this means like you can set your target response spectrum, and we have our time history analysis record, and then we can match the response spectrum and our time history analysis record, and then utilize those for the time history analysis. So for that you can choose different codes that you are following in order to develop your models. So for example, like I'm a little bit familiar with the the Indian standard code, so I'm trying IS 1893 2016 and then click on add new function. Now we can give you the name like target response spectrum. So here basically we designed for the seismic zone B5, which is the most prone to the earthquakes, right? So and then these are the inbuilt values that is defined by the code. For example, seismic zone 0.6, importance factor, soil types, reduction factor, and so on. So and for the damping ratio of 0.05. So we define this as a target response spectrum and click on OK. Then the next part is we need to for the time history we go to the define, functions, and the time history. Then from here we have the option like how to choose your function. So you can save, you can use your saved time history analysis record. So for that we go from file, add new function. So there are a couple of options, like for example, one, if you have your records you can save in your computers and you can upload here. If not, then for example for the El Centro, the ETAPs, they have the El Centro inside the ETAP software. For example, we go to the browse, then if we go to the time history function here, then they have the ETAPs also have a multiple recordings here including the El Centro. But I'm trying to the same El Centro, but I'm trying to use here in the both directions, like in the X direction and the Y directions. So I have the recording here and I have downloaded to my computers. So I will select first El Centro data NS directions. So this is the web in the NS directions. You can see the files from here. This is generally a txt file, right? And then they have the recordings, and I just save it as an interval of 0.02. So this is the value interval of 0.02. Then we don't have any headers in the file, and the data per line is only one. So this is our El Centro data in the NS directions. We click on OK. We can see our file here, and similarly we again do the similar procedure for the EW direction. Again for the same 0.02 the equal interval. We click on OK. So now we have defined the our accelerations and time data. For example, like taking the reference as a El Centro earthquake data in the NS direction and EW directions. So after that we need to match our defined target response spectrum and the time history analysis data. So for that we can again go to define, function, and time history. Then from here again we can select the match to response spectrum options and click on add new function. So after that we give some name to it. For example, let's say time history analysis. Okay, and they have the options like whether you want to do matching in the frequency domain or the time domain. So this time I'm trying to select the matching in the time domain, and then we need to give which is your target response spectrum, which we initially defined before as a target response spectrum, and the reference acceleration time history. So this one is let's select the NS. So let's give the NX as Y. in the name frame THAY. Okay, and we need to be very careful with these units. For example, like the target response spectrum is unit is in acceleration due to gravity g, and our time history analysis is which unit. Our time history analysis record is in the centimeter per second square. So, and then after that you can change the matching parameters here, but I keep it all as default values, and then we click on the match time history. So it will take a little bit time. So we can see that this is our target response spectrum, and this is our the time history, the records, which is the El Centro earthquake here. Sorry, it's taking a little bit time. Please wait. Okay, so now you can see that I mean here the blue line means that the time history records, and you can see that the red line here is the matching our the target response spectrum, right? So we just click OK. So in the similar manner we also try to match in the x direction. So again we click on add new functions. So we give the name here as THA in x directions, and selecting the matching spectral in the time domain. So here target response spectrum and time history analysis. Now we select the EW directions. So again we change the unit to centimeter per second square, and we click on match time history. So again it will take a little bit time. Okay, so now we can see that it's match in the x direction also, like match with our design spectrum. Then we click on OK. Sometimes the matching is not done, or if there is a huge variation, then we can also scale up, and then we can somehow match with our design spectrum. So we have now in the x direction and y direction. We click on OK. Then after that we need to define this as a load cases. So we go to the define load cases. So from here add new case. So we give the name as time history analysis, and the load case type we select time history, and whether you want to do a linear or non-linear models. I select the non-linear model this time. Then we will add function or the load here. For example, the load pattern is accelerations in the u1 directions, and we select the we select our the match the response spectrum. For example, this is in the x directions, and the scale factor basically means that in the code they have given that the scale factor is generally calculated as the formula that I multiply by g by r, which means that I is the importance factor, g is the acceleration due to gravity, and r is the response reduction factor. So the importance factor here is considered as 1, and for the acceleration due to gravity we need to check the units. For example, the acceleration due to gravity units here, you can see that the mm per second square. So if it is in meter per second square, we consider 9.81, and mm per second square means we consider 9810, right? So it basically means that 1 multiplied by 9810, sorry, 9810 divided by the response reduction factor is 5. Similarly, we do the same in the y direction, select accelerations, then we have considered u2, time history analysis in the y directions, then again the scale factor, same, 1962. And then the number of output time steps means that the total time step of our acceleration time history data, and then if you divide by the output time step size, then you can get the number of output time steps. So for that you can again check how much is the total time for our models. For example, if we see the functions, time history, go to the EW modifier so function, then we can see that it's around almost 54 seconds, right? So we can assign the same here, lowercase go so and modify. So if it's 54, then we divide by 0.1, then it's 540, right? 540, and then we click on OK. So we define the time history case, including both in the x and y directions. Click on OK. Then after that we'll do analysis. So for that we go to the analyze. Initially we will check our models whether is there any discontinue in the connections or something. We click on OK, then it will analyze and we shows us if there is some warning, then it will give us the message here, then we need to check our model accordingly. But now the model has been checked and no warning message was generated. So then after that we go to the set load cases to run. So I will select all the other cases as do not run. So dead load as do not run, live load do not run, models, and so we only consider the models and the time history analysis as a run. Then I go to run now. Yeah, so now the analysis has been completed. So if you want to see the animation, you can do the start animation and all. So but I will go to display and show story response plot, right? So from here you can see that the response of the building structures in this earthquake. So this is the model case. So you can see the display size, maximum story displacement, and the case is model, but I'll select here time history analysis. So it's showing 0 for all the 0 time steps. So if I select as a maximum and a minimum, you can see that this is the maximum story displacement. So blue means in the global x directions, and the red means in the global y directions. So after you have the maximum story displacement from here, you can also check the maximum story drift for the building structures. You can get the maximum value from here, 0.00256, and you can check the limits with corresponding to your threshold value that is defined in the building codes and standard, and then you can classify your building structures. So for example, like you can take the maximum story drifts or maximum story displacement. After you have the results from here, then let's go back to our slide. Okay, so you have the story displacement. For example, like this is the buildings, then you have the story displacement d1, d2, d3, d4, d5, right? That is with respect to the ground. Then you can figure out the interstory drift. The first case is the same as the story displacement. For the second case, the d2 minus d1, and so on, we go to the upper floor. Then you can simply calculate the interstory drift ratios dividing by its story height, and you can get the maximum interstory drift ratios. So having these values, then you can define the different damage cases into different categories. For example, in my previous study, I classified into the 5 different categories from no damage to the collapse. But for this lecture, I'm trying to use only 3 damage categories, considering these 2 as a safe or the slight damage, and the heavy damage considering as a limited entry, right? Only the limited entry, and then the last 2 case very heavy and the collapse considered as the unsafe damage categories. So so you can save your data as a CSV file. For example, like you can get your PGA, or maybe you can also consider more structural more seismic parameters like PGV or spectral accelerations and so on. But for this study, I only took the PGA. This is the random value that I generated in the Excel and saved as a CSV file, and also the random value that assigned for the different number of stories. And this is the height that we get after multiplying by 3 to the number of stories. Then we get the height of the building structures. Then we can also calculate our plinth area of the building structures, right? And based on the analysis result, you can classify into the 3 types categories. 0 means like safe, 1 means limited entry, and 2 means the unsafe damage case. So after that, how to use this data to train the models and have the and try to classify the buildings into different categories. So for that, I want to show you demonstrations in the Google Colab. So for that, what we do is initially we need to define some our input some libraries here. Input numpy as np and the matplot library, basically used for the plotting of the graphs and so on. Then after that, we need to mount our Google Drive where we have saved our data and the folder, right? So for that, we mount our drive, and then we define the path using the OS library. Then after that, we can import our data as using the panda, where you can simply do pd.read csv and read your csv file name here. Then you can check the data info. For example, here I have 5 different columns: PGA, NS, the number of story, height of the buildings, plinth area, and the damage class. I have together 100 randomly generated data sets, and you can also check the type. Then simply if you do data.describe, then you can also get the minimum value, maximum, standard deviation, mean, and so on. So this is the data that I am considering for this lecture. So I have together like 100 data sets and different value of PGA, number of story, height, plinth area, and damage class. So I have 33 for the 0, 35 for the 0, 33 for the 1 class, and 32 for the, so it looks like somehow similar data sets or the balanced data sets. Then you can also use the heat maps in order to see the correlationship between the damage features. You can see that the number of story and the height, they have almost one, means like they are highly correlated because it's directly proportional, almost the same, right? This is the number of story is 5, means if you multiply by 3, then you get 15. So it means like if you multiply by constant, then it's almost a similar value. So it's showing the higher correlationship between these 2 features. And you can also use the pure plot function to check the relationship between the input features. So here I define the input as PGA, number of story, height and plinth area, and then the damage level is the damage class. And then before that I did the data normalizations, so that every data in the lecture in the data sets, they will be between 0 and 1. Then we can simply split our total damage data set into the training and the testing. So the test data set is 30% and the training is 70% here. Then I try to build a very simple architecture of artificial neural network using the Keras library. So here I use input as 4 and the activation ReLU, and one hidden layer, and then the last layer is dense layer with the 3 output cases using the softmax activation functions. Then the model is compiled using the optimizer Adam, loss as sparse categorical cross entropy, and then matrix as accuracy. You can summarize your models. Then the next part is the feed the models. So I try to feed the models here using the training data sets with 20 epochs and batch size of 8, then using the validation data set that test data. So with that, for the you can also plot your accuracy and the loss curve. So this is the loss of training and the testing data sets, and this is the accuracy for the training and the testing data sets. Not looks good because this is a very randomly generated data sets, and so if we try to evaluate, then it shows the accuracy of around 0.43%, right? Then you can predict your test data, and the model.predict test data, you can see the Y predictions. So if you print Y prediction, then you can see this 3 data in a row, right? So further what we need to do is we just choose a maximum value from this row and assign to this class. For example, here if you check this first row, this one has the maximum value. This is the maximum value, so it means like this is 0, 1 and 2. So this is one class, right? So if you see this is one class, and similarly we get the damage class for other cases too. Then at the end we plot the confusion matrix, right? For example, you see that the 4 are correctly predicted as a safe class, 6 correctly predicted as the limited entry, and 3 correctly predicted as the unsafe class. You can also print the classification reports like this, where you can see the precision, recall, funny score, and your accuracy. So this is the general demo utilizing the artificial neural network. In the similar manner, you can do for different classes, considering more structure and the seismic parameters, and considering more structure and the parameters, and also maybe you can generate simulation datasets in other way as well, right? So if you are more interested in this area, then we have recently published a paper in engineering structural dynamics, where I generated data using the for example, like simulation dataset to train the models, and then validate the models using the real world damage dataset that is collected after 2015 Nepal earthquake. Then in the next paper, utilizing only the real world damage dataset, and we'll try to classify the building damage into 5 different categories and 3 different categories. And in my next paper, I try to utilize not only the real world damage dataset, also the finite element model results, and also the results that is generated utilizing the some simulators, real-time simulators, which is called U simulators, that is developed by Beijing Earthquake Administrations. And currently I'm also trying to use the quantum enhanced machine learning algorithms, and then compare with the other classical machine learning algorithms based on the performance on real world damage datasets. And this paper gives you the general ideas about using the convolutional neural network utilizing the damage images. And here I am trying to utilize the quantum enhanced convolutional neural network in order to classify the building damage images into different categories. And at the end, I'm also trying to compare other pre-10 CNN architectures, and then compare the results. and we have published this paper. If you are interested in more details in this area, then maybe you can refer to these papers, or maybe you can also contact me. We can work together. And I wish you all the best. Thank you very much for listening.